So welcome everybody to this latest video on 162 Maths, and in this video we'll be going over the GCSE Maths higher topic of geometric proof and going over some key principles of what you need to revise to understand this topic a little bit clearer before going through some past exam questions. Now, as always, there'll be a copy of the questions in the description below for you to have an attempt at before watching through this video as we go through the answers, and I'll also include the mark scheme just in case you find an alternate way of getting the same answer which differs from the one that I go through in the video. Now, geometric proof is classed as a higher level topic, so in other words you tend to find that these questions tend to appear at the latter end of a higher GCSE paper. Now, what makes geometric proof difficult questions, or most students find difficult, is because they don't really know how to get started. But one of the key things of how to get started with geometric proof questions is to try and remember and sort of collate everything you know about angles and geometry. Now, before tackling through some past exam questions, let's just run through some of the key elements of what you actually need to revise and recall when approaching some geometric proof questions. Now, the first thing we're going to look at is angle properties. So this stems from all the way back to basic Key Stage 3 in primary school, facts about angles. So knowing that angles on a straight line add up to 180, angles around a point add up to 360, and opposite angles are the same, so they're going to be equal to each other. Now, the next step from those is recognizing angles on parallel lines. Now, it's really important that along with some most geometric proof questions, you kind of need to write down and show that you are understanding about what rules you're actually using to know what angles equal what. So it's really important that you use key vocabulary like corresponding angles when representing what we used to call F angles. And again, remember that F could be both in normal orientation, or it could be reflected or rotated. So it's not just a case about looking for, let's say, the blue angles. You've also got to look at the red angles, but also recognizing you can have an upside down F. So this angle here would be the same as that angle there. And if I get another color, let's go for orange, and that this angle here is going to be the same as that angle there. Another key rule with regards to parallel lines is alternate angles, so formerly known as Z angles. So again, knowing that they are both equal, and again, it's also established that Z angles don't necessarily need to look like a Z. They can look something like this. So here we could have an angle where this angle here is going to be the same as this angle here. Now, the key thing, remember, with regards to using any of these two rules, and we're going to move on to co-interior and supplementary, is to make sure that you are fully aware that those lines are parallel. So they'll either be represented by two arrows, or it will state it in the question, so form of, let's say, parallelograms, or things like certain shapes that have to have parallel sides. So in other words, things like shapes like trapeziums, etc. And the last one we look at with regards to angles on parallel lines is co-interior and supplementary. Now, unlike corresponding and alternate angles, these angles are not going to be the same, but they do add up to 180. And the key principle of that, remembering that, is to just use basic angle facts of when you've got supplementary angles or co-interior angles, one angle is going to be acute, the other angle is going to be obtuse. So they can't be the same because they're two different types of angles. Now, the next thing we move on to is properties of polygons. I don't know why I've just attempted to cross that out, because I thought I had a highlighter. Now, properties of polygons. Now, this includes basic geometry properties of polygons. So things like recognizing that a square has equal sides and two sets of parallel sides. A rectangle has got two different sides of lengths of sides, of opposite sides, but also all the interior angles are going to be 90 degrees. Things like recognizing what makes a trapezium different to a parallelogram, what makes a difference between a rhombus and a parallelogram. So just basic key properties of polygons, notably things to do with the sides and the angles in there as well. Now, the next thing we move on to is angles in triangles and polygons. So it's really important that you're able to establish and know that, obviously we know that angles inside a triangle, any triangle, have a total sum of 180. But when you've got an equilateral triangle, and this is usually represented when there is markings on all three sides to imply that they're all equal length, that the angles inside the equilateral triangle are all going to be 60 degrees. And with an isosceles triangle, not only have you got two sides the same, you're also going to have two equal interior angles as well. And it's really important that when you see or can see an isosceles triangle, that you know which two angles are going to be the same and which one is going to be unique, because sometimes it's not that obvious, and it's really important that you do establish which is which. The next thing we move on to is angles in a polygon. Now this doesn't need to be a regular polygon, but if you want to know the total sum of angles inside any polygon, so whether it be a quadrilateral, a pentagon, a hexagon, a heptagon, etc., then we can generally use this rule here, which is 180 multiplied by the number of sides take away 2. So here we've got a 5-sided shape, so to work out the total sum of angles inside this shape, it'll be 180 times 5 take away 2, which is 3. Another way of doing it is to remember it is to pick one point and then draw straight lines to each of the other corresponding points, and then you'll turn that into interior triangles, and you know that each triangle has a total sum of 180, and then you just multiply by how many triangles you could see, and you get the total sum of angles. Now the next thing on our list to remember is circle theorems. So you need to remember all of the circle theorems, and particularly you know when a geometric proof question involves a circle theorem when you basically see a circle and things inside it and potentially a few things out of it. Now when it comes to circle theorems, it's really important not only that you are able to know each of the rules or the theorems, but you also know word for word what it is and how to prove it. Now remember, with the alternate segment theorem, that is probably the only exception that you can get away with just knowing the title of the circle theorem. For all the others, you kind of need to know some formation of what it actually is. So you kind of need to remember, just like you would in any other sort of subject for GCSE, like history, where you're remembering certain phrases and key properties in science. Well, for maths, it's the circle theorem, so it's really important that you're able to know those. The next thing, what helps with circle theorem questions and relating to, because there are so many, is just being able to spot what it is you're looking for. So if you see a triangle where all the points are on the circumference, it's going to be a good chance it's going to be the alternate segment theorem or angles on a semicircle. If you're seeing an arrowhead, again, it's going to be the arrowhead theorem. If you're seeing a bow, again, you're using that theorem. If you're seeing tangents and radiuses, then again, it's looking at that. And also, if you're finding a quadrilateral where all the points are on the circumference, then you know it's going to be a cyclic quadrilateral. So these are the key things that can help you make those questions just that little bit easier. And the last one is looking at exterior and interior angles of a regular polygon. Now remember, with exterior angles, that all exterior angles add up to 360. So it's going to be 360 divided by n, where n is the number of sides. Now if you're looking at the interior angles, well, the formula for the interior angle of a regular polygon is 180 n minus 2, where n is the number of sides, divided by n, and that'll tell you what the interior angle of a regular polygon. Now remember that exterior angles, that's slightly different, but with interior angles you really do need to make sure that it's stated in the question that it's a regular polygon where all the sides are the same in length, or it's marked on the diagram with simple little notches on each of the lines. Now, as always with many of these walkthrough videos, that if you're wanting to have an attempt at these questions before watching through this video as we go through the answers, then all you need to do is to simply click on the link in the description below and you'll have access to these questions. Alternatively, if you don't have the opportunity to print out any of the questions, then all you need to do is just simply pause the video as I read out the question, have an attempt at it, and then unpause to see as we go through the answer. So let's have a look at question 1, and let's zoom in so we can actually read it properly. Now, with just a quick note before we start with all of these questions is that I'm only going to be showing you kind of one way to get to the answer, in which there may be multiple ways of getting the correct answer, but I'm just going to use the one that comes straight into my mind to try and help you, and hopefully it's going to be one that's going to be most popular and the one that's most efficient. But if you do find that you've found another way of doing it, or you may have gone the quicker way or maybe a bit longer way than what I've done, then I'll include the mark scheme in the description, in the link, so you can see whether you would get the marks for it. So let's get started on question 1. So question 1 says A, B and C are 3 points on the circumference of a circle with centre O. BD and CD are tangents to the circle. ABC DC is a kite, and angle BDC is X. And the question we need to ask, or the question they're asking, is to prove that angle ABO is 45 minus X over 4. So let's first of all make sure that we're making a note of what that angle there is. So let me just highlight, and they've highlighted it kind of in the question but not made it sort of explanatory. Now I can't call it X, but this is the angle of ABO. So let's get started on what we know. Well, looking at this question, I can see that I've got a tangent because it says it there, and I know that I've got a radius. So therefore I know that these two angles here are going to be 90 degrees. And again, what you might want to do is just say how you've got those. So if I just label this as 90 and that is 90, and then a radius meets a tangent at 90 degrees. Now from there I can then work out what this angle here is going to be. So this angle here is used, and then what I'm going to do is I'm going to use the angles in a quadrilateral add up to 360. So this angle here is going to be 360 minus 90 minus 90 minus x. And so if I simplify all of that, I get 180 minus x. So this angle here, I just get rid of that little line there. So that there is 180 minus x. And then I can just draw the line from where that is. So once I've got that, I can then know that this angle here, so you can see I've got an arrowhead, well that's going to be 90 minus half x. And the reason for that is because we're looking at the arrowhead, so it's the angles, shall I say angle at the center is twice the size of the angle at the circumference. Now I may not be using the correct word for word explanation that you may have, but something along those lines would be absolutely fine. So then from this I can then work out what those angles there are going to be. Now for this angle here, well, we know that it's a kite, so this angle, that side there and that side there are going to be equal, and this side and that side are going to be equal as well, because it tells us that it's a kite from this here. Now in a kite, opposite angle is going to be equal, so from this we can then work out what angles in, so from this, get different colour, so this angle here and this angle here are going to be the same, and we know that angles inside a quadrilateral, so inside the kite, are going to be equal to 360. So here we've got 360. Now if I just call this purple angle y, then that's going to be 360, take away 90 minus a half x, and just put that in brackets, minus 2y minus x, well that equals, I should say, plus x. So from this what I can then do is I can then work out y in terms of x. So from this what we've then got is 360, and we've then got equals 90 minus a half x plus 2y plus x. So then what we've got is we've got 270 equals, it's going to be a half x plus 2y. So then from that what I've got is 270 minus a half x equals 2y. So y is going to equal 135 minus a quarter x. Now from this, if that's what y is, then y consists of ABO plus 90 degrees. So then there, what I've then got is ABO equals 135 minus a quarter x, and then I've got this 90 that I need to get rid of, which then equals 45 minus 1/4 x, so it's 45 minus x over 4, and there is my final answer. Moving on to question 2, it says ABCD is a quadrilateral. Prove that ABCD is not a cyclic quadrilateral. Now with this particular question, what we need to do is we need to state what rule we're going to stay in. So if ABCD was a cyclic quadrilateral, then opposite angles will equal 180 degrees. So this is the fact that I'm going to be using. So what I need to do is I need to show that diagonally opposite angles do not add up to 180. So I just need to work out those two. Now first things first, what I need to do is I need to find x. Now one thing I know, whether it's a cyclic quadrilateral or just a quadrilateral, that all the angles inside that shape need to add up to 360. So here I've got 4x plus x plus 36 plus 92 plus 5x plus 30 equals 360. So then what I've got to do is just neaten all of this up. So I've got 4, 5, then 10. So I've got 10x plus, and then if I've got 36 plus 30 plus 92 equals 158. And that equals 360. So 10x is going to equal 360 minus 158, which is 202. So x equals 20.2. That's a fact. So now what I've then got to do is to now see if the opposite angles add up to 180. So when x equals 20.2, this is going to equal 4 times 20.2, which is 80.8, and this here is 90. So as 92 plus 80.8 does not equal 180, ABCD is not a cyclic quadrilateral. So again, it's really important that you do state this, you show the mathematical evidence in terms of the calculation, and then you do write your closing statement by just reiterating what it is you want them to prove. Moving on to question 3, it says PQR and S are points on a circle, PXR and QXS are straight lines, PX equals SX, and the question is asking us to prove that QS is not the diameter of the circle. Now again, looking at diameter, you think to yourself, well, okay, which circle? I can see a circle. What circle theorem involves the diameter? Well, it's the semicircle rule. So if QS is the diameter, then this angle here, so QPS, will equal 90 degrees. So this is the rule that I'm going to be using if it is 90 degrees, if QS, sorry, is the diameter. So let's have a look at actually working this out. So let me just get rid of that angle there. Now from this, I can see that this angle here is going to be 27 degrees. And how do I know that? Well, it's a bow. And again, I could say that angles that share the same segment are going to be equal. So that's going to be 27 degrees. The next angle I can then work out is this angle here, because it says that this triangle here of PXS is an isosceles triangle. And again, I've not marked those lines. It's already marked on the diagram. Just to show that I'm not lying, let's just get rid of those. You can see two faint lines. Then these two angles here are going to be equal. And I can work that angle out by doing 180 minus 50 divided by 2. So it's going to be 130 divided by 2, which is 65. So this angle here is 65. So therefore, that angle QPS is going to be equal to 27 plus 65. And that comes up to a total of 92. So as QPS is not equal to 90 degrees, QS is not the diameter. And there we go. Now the reason I've got to use that one because I've got no indication about any length, so I can't work out the diameter of looking at the radius or things like that. There's no indication, and that helps me to use that sort of key property to answer this particular question. Moving on to question 4, it says ABCD is a quadrilateral, sides are extended as shown, and the question is asking us to show that x equals 100. Now in this particular question we can't see a circle, so it's not going to be related to any circle theorem, so it's just going to be a case of just knowing just basic angle facts. So x is what I'm trying to find, so looking at this I can see an opposite angle, so I know that this angle here is going to be 70, and if I wanted to I can just write down y. I know that it's equal, so that's going to be 70. I can then work out what this angle here is, because angles in a quadrilateral add up to 360, so this angle here is going to be 360 minus 90 minus 120 minus 70, and if I work that all out I get an answer of 260. And let me just double check because that doesn't seem right. 90 minus 120 minus 70. It's actually 80. And then I can then work out what angle x is. So x equals 180 minus 80. So x equals 100. And again, the reason I've used this Swiss one is angles on a straight line add up to 180, so x equals 100. Moving on to question 5, it says the diagram shows a triangle and a trapezium. Prove that A equals B. So looking at this, what I'm wanting is, well, I can see that if I use the angles around a point add up to 360, but the problem is I'm going to have something involving A, which is fine, but C, and I don't want C because I need B instead. So then from this, what I can then know is that C and B are co-interior. And again, that's labelled by the reason why it's a trapezium, but I also know that these two lines are parallel. So this angle here and this angle here are going to add up to 180. So that means that C is going to be equal to 180 minus B. I'm just going to put a little box around that. Then using this key property here, what I've got is I've got A plus 65 plus C plus 115 equals 360. Now instead of writing C, I'm going to write 180 take away B instead. So I've got A plus 65 plus 180 minus B plus 115 equals 360. Then if I neaten all of this up, I get A plus, and it's going to be 65 plus 180 plus 115, which gives me 360 minus B equals 360. The 360s cancel out, so I've got A minus B equals 0, and then take the B over the other side, and I've proved that A equals B. Moving on to question 6, it says that ABCD is a parallelogram. Work out the size of angle X. So with the parallelogram, I know that this angle is going to be the same as this angle here, and this angle here is going to be the same as that angle there. So this entire angle there is going to be 4x, but let's just have a look if I actually need to know that. So angle X is what I'm trying to find. So let's first of all look at the triangle ABP. Now this triangle here is an isosceles triangle. So that means that this little orange angle that I've highlighted is going to be the unique one. So this is going to be 51. And so to work out what angle this is going to be, it's going to be 180 minus 51 minus 51, which gives me an answer of 78. So that angle there is going to be 78. I also know that this angle here is going to be 78. Then let's have a look at the next one. So from this, I can then work out what this angle here is going to be. So let's just use different colours. So this angle here is going to be 180 minus 51, which gives me an answer of 29 degrees. And then let's have a look at how we'd work out the others. So we know that this angle here, this green angle, let me use a different colour. Let's go for purple. That this angle here is going to be 4x. It's going to be 4x minus 51. So then from this, what we can then do is we can then work out what the angles there are going to be. Well, actually, let me just get rid of that because I've just spotted another way of doing this. So this angle here and this angle here are going to be the same because it's a parallelogram. So that's 4x. So this is going to be 4x. And then we know that angles inside a quadrilateral add up to 360. So what I've got is I've got 360. Well, let's not write that. So I've got 4x plus 78 plus 4x plus 78 equals 360. Then if I neaten this up, I get 8x plus 156 equals 360. So then 8x equals 360 minus 156, which gives me 204. And then dividing both sides by 8, I get an answer of 25.5 degrees, and there is my final answer. Moving on to question 7, it says that ABCD is a parallelogram and CE equals CF. Prove that Y equals X. So looking at this diagram, I can see I've got a parallelogram and I've got an isosceles triangle. So looking at this angle here is also going to be Y. So therefore I can then work out what this angle here is going to be by doing 180 minus 2y. From this, what I can then do is I can then, knowing that ABCD is a parallelogram, so this angle here is also going to be 2x. So then from this, I now know all the 4 angles around this point, in which it's going to be 2x plus 90 plus 180 minus 2y plus 90, all add up to 360. Then neatening all of this up, I get 2x plus 180 plus 180 minus 2y equals 360. This equals 360, so that just becomes 0. So 2x minus 2y equals 0. Take the 2y over to the other side, then divide by 2, and end up with x equals y, which is what they wanted me to show. Moving on to question 8, it says that the diagram DC is parallel to AB. Show that the angle ABD is isosceles. So in this particular question, there is no indication that this is a parallelogram. So we can't just assume that opposite angles add up to are going to be the same. In fact, that they don't actually add up to the same, because this side here plus this side here do not add up to give us on the same. So let's have a look at the key bits of principle that we do know. Now, we know that it's parallel, so it's going to be parallel lines. So from this, I can see a Z angle. So I've got one Z that is here. And do I know any of those angles? Well, I can work out what this angle here is going to be, because angles inside a triangle are up to 360, so that's going to be 180, take away 100, minus 52. So that's going to equal 28 degrees. So then this angle here is going to be 28 degrees. And then from this, I can then work out what this angle here is going to be, because again, I could do 180, take away 28, take away 124. And if I work all of that out, I get an answer of 28 degrees. Now, going back to the question, it says show that ABD is an isosceles triangle. So ABD is this triangle here. So here, what we can then say is as ADB is equal to angle DBA, then triangle AB CBD is isosceles because we've got two equal angles. Moving on to question 9, it says that a parallelogram ABCD and a triangle DCE are joined as shown. BCE is a straight line, and the question is asking us to show that DCE is an isosceles triangle. So if it's an isosceles triangle, then basically two angles must be the same. Now we could say two lengths, but we've got no indication about what any of the lengths are, so we can't use that. It's going to be two angles. So knowing that it's a parallelogram means that opposite angle is going to be the same. So that's going to be 105. And from this, I can then work out that it does say that BCE is a straight line. So this angle here is going to be 180 minus 105, which gives me an answer of 75 degrees. I can then work out what this third angle in the triangle is going to be, because angles inside a triangle up to 180. So 180, take away 30, take away 75, and that's going to give me, what, 105, so that equals 75 degrees. So then, just like we did in the previous question, we can then say as CDE is equal to DCE, the triangle DCE is isosceles. And there we go. Moving on to question 10, it says show AB is not parallel to CD. So here, if AB was parallel to CD, then x plus 120 would equal 180 because they're co-interior or supplementary. So this is the general rule that I'm going to be using to prove whether this is true. So the first thing I need to do is I need to find x. I'm going to find x by using this diagram here and knowing that all those angles added together in a quadrilateral add up to 360. So here I've got 360 equals, and it's going to be 6x plus 60, and so 300 equals 6x, so x equals 50. So knowing that x equals 50, I can then work out what this is. So here, as x equals 50, 50 plus 120 is not equal to 180, so AB is not parallel to CD. Then moving on to our last question, it says that PAQ and PB are tangents to the circle and that AC is equal to BC. And the question is asking us to work out the size of angle X. And we must show our working, which may be on the diagram, which is massively helpful. So first things first, we know that I can see that I've got a tangent and I've got a triangle. So we can know straight away that this angle here and this angle here is going to be the same. And the reason for that is because of the alternate segment theorem. Now from this we know that it tells us that AC is equal to BC, so and it's marked on the diagram, which means that triangle ABC is isosceles. So this angle here is also going to be 52 degrees, and the reason for that is because it's an isosceles triangle. So I can then work out what this angle here is going to be, and that's going to be 180 minus 52 minus 52, which is 104, so that's going to be 76 degrees. And then from this we can then work out what the angles are going to be. So from this we then know that, and we know that the line PB and PA are tangents to the circle, which means that these lengths here are also going to be equal. So that means that triangle APB is going to be isosceles as well. I can work out what this angle here is, because that's going to be 180 minus 52 minus 52, which is 76 degrees, which means that this angle here is going to be 76 degrees. So then to work out what x is going to be, x is going to be 180 minus 76 minus 76, so x equals 180 minus 152, and so x equals 28 degrees.